In a world where 7 equals 0.
Hello, and welcome to Unnatural Numbers, the chat show where we finally try to understand absolutely everything about one single number. Today is episode 2, where we're going to learn how many people really are required to tango. Joining me today as my guests, we have Professor Jim Fowler, who is Associate Professor of Geometry and Topology at The Ohio State University. That's right, folks, The Ohio State. And we also have Cindy, who is an undergraduate at King's College London, who finished her exams about a month ago and has just been reading up on the number 2 for this whole time up until now. And I'm, of course, Ben Cornish, not a real mathematician, just two physicists wearing a trench coat. So today we're going to be digging into the number 2, and up first, I believe, is my fact. So before I start my fact today, I'd like to ask you both a question. If I gave you both calculators and started dictating a calculation that was only comprised of numbers, pluses, minuses, and divides, do you think by the end of it you'd have the same answer?
I completely believe that we would now.
Well, so my fact today is that actually the total number of solutions that you should get from this calculation is 2 different answers. What? And we're going to have a look at
No.
why that is true in a sense. Now, like all good facts, this one is in fact a lie. But by exploring the lie, we can hopefully find out a little bit more about what's going on here. So on the board here, I'm going to start by defining a little guy x. And I'm going to say that x is going to be equal to 1 plus 2 divided by 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 1 plus 2 divided by... And I'm actually going to just keep that going forever and ever and ever. And we're going to see what the result of all of this is. So this is what you might call a continued fraction. We've got lots of fractions that are embedded in other fractions, and it just carries on going forever and ever. It's a continued fraction. And so it's not immediately obvious what the answer would be if you just started typing that into your calculator and carried on going forever and ever and ever. Now, I know what you're thinking. I know what you're thinking. You're saying that 1's a positive number, 2's a positive number, adding is, well, if you add a positive and a positive, you get a positive. But the result of all of this calculation is actually -1. And it's a bit weird, isn't it, to say we're only adding things up, and yet the answer is -1. I know, it's a healthy amount of skepticism. But watch this, watch this. Inside this very first layer of the embedded fraction, we've got something that looks familiar. In fact, I could zoom in at this point, and it's exactly the same thing as we started with. 1 plus 2 divided by 1 plus 2 divided by 1 plus 2 divided by. So this whole calculation, really I could say it's x is equal to 1 plus 2 divided by x. And that is going to let me test my statement at the start. I said the answer to this, the value of this, was -1. So grab your calculators, folks. What is 1 plus 2 divided by -1? Well, clearly it's -1.
-1.
And therefore, cha-ching, answer is valid. Oh, no, I know. You're thinking, surely this can't be right. This is so unintuitive. But I reckon I could demonstrate it to you with a proof. So let's see if I can prove this one. What I'm going to do is I'm actually going to rearrange this calculation. So I had x in both parts. I'm going to rearrange that and turn it into something a bit more familiar. So if I multiply both sides by x, I should get x squared is equal to x plus 2. And then I could rearrange that all onto the left-hand side to get x squared take away x take away 2 is equal to 0. And that, well, that's our good old friend, a quadratic, isn't it? And if I solve this quadratic, I think I should get, well, let me factorize it. I get x plus 1 times x take away 2 is equal to 0. And bam, the answer is -1. Do you notice anything questionable about that?
Answer is 2.
Sorry, what? Yeah.
Well, maybe the answer is 2. What happened to the other root?
Oh, this one. Oh, yeah. So,
Yeah.
do you know what? Given that today's episode is all about the number 2, maybe we should just entertain for a moment the idea that maybe the answer could be +2 as well. And in fact, +2 feels a little bit more intuitive, doesn't it? Because all we had was adding,
Getting bigger.
and all we had was positive numbers. It should get bigger. Yeah, exactly right. So where did this? What's happened to this other one? Well, let's just check it first of all. Does it really work if we replace this value with a 2? Well, 1 plus 2 divided by 2 is 2. Yeah, so that also works. It definitely works. So how do we know which one's correct? Are they both correct? Is one correct? I'll tell you. Let me see if I can give you a slightly different formation of a continued fraction, and you can tell me what you make of this one. So for this one, I'm going to go with x is equal to 2 subtract 2 divided by 2 subtract 2 divided by 2 subtract 2 divided by 2 subtract, etc., etc., etc. So this is another infinite fraction. This time I've gone entirely with 2's because it is thematic. Today's episode is all about the number 2. Well, how are we going to work out the value of this one then? Should we use the same trick? Yeah, if we've found a method that we like, we may as well use it until it breaks. We can say x is equal to 2 subtract 2 divided by, and then all of this we can just replace with the letter x. And I can solve that. That's just going to be another quadratic. It's going to be identical, really, in form to the one above, surely, because this is just a quadratic. So we get x squared is equal to 2x take away 2. Feels very safe, very, very safe. And maybe I could ask one of you guys to solve this one for me. What happens if I move that all onto the 2x, move this all onto the left-hand side? What's the values of x for this, please?
Oh, it's a
Oh, what?
imaginary
So
number.
a hesitation, you say? Did I hear you say 1 plus or minus I, where I is
I'm
the
more
imaginary
worried about
constant?
this.
Hmm. Because this time, it is only real numbers that are being subtracted and divided. And yet, for some reason, not only are there two distinct solutions, but those solutions are complex. And this just feels like it's breaking maths, doesn't it? This is not very pleasant. So we're gonna have to figure this one out. And I think in order to figure out the system, in order to work out what's going on here, it might be beneficial for me to try to engineer a problem that we could then solve. So we know that we're going to be expecting two roots, and we know that we would prefer them to be positive. We'd prefer them to be real. I don't know if we care whether or not they are whole numbers, whether they're natural numbers, or if they're something else. But we definitely want them to be real and preferably positive. So let me introduce another one to you then, and I'm going to design this one myself. I'm going to say x take away 1, open brackets, x take away 2 equals 0. So I'm going to start from the end and say those are that is my quadratic. Those are my solutions. I've got solutions 1 and 2. They're both real, they're both natural, they're both positive. If I were to expand this, I get x squared take away 3x plus 2 equals 0. And I can rearrange this by adding 2, taking out a factor of x and dividing and adding the 3. And you should end up with 3. Let's see, this is 3 subtract 2 over x. If you don't trust my arithmetic there, because I did it in my head, you can pause the video now and check for yourself. So I'm designing a continued fraction now by setting it up in this quadratic form. And I reckon just for the people out there who like me to write out things in full, this is going to be 3 take away 2 divided by 3 take away 2 divided by 3 take away 2 divided by 3 take away 2, etc. And I suppose we do have some subtraction, so maybe it would have been okay if they were negative, but we know both solutions are positive. So how do we know which one is correct? Can it be that two things are correct? They both feel intuitive, they both feel plausible, but surely a calculation should only have one answer, given it is just a repetitive case of typing in numbers into your calculator. You should have to get the same thing. That's kind of one of the fundamental things about maths. We always get the same answer if we follow the rules. And there's the problem, because I've not really been following the rules. What we have here is what you might call in philosophy a category error, in that I've asked a question, but I've suggested that the question belongs to a category that it doesn't. It would be like me asking you, what does the number 2 smell like? It doesn't have a smell, it's a category error. Here, I'm suggesting that the solution to this calculation exists if we consider it to be a quadratic equation. But really, it's not a quadratic equation. It is actually just a repeated calculation with fractions that go on forever. And because it goes on forever, the proper way to deal with this should actually be in the form of a sequence. So in this sequence, we are going to start with what we think might be the solution to the problem. Let's say I think the solution is not 1, not 2. I think the solution is actually 3. And I'm going to say x naught is equal to 3. And now I'm going to use the setup that I've devised over here to create a recursive sequence where I
You're
can
just
say that
guessing to
x.
start with 3.
I just started anywhere I
Just
liked,
started
to be
anywhere.
honest.
Okay.
Yeah, just as long as it was a real number, I'm just starting anywhere. And this should always get us back to a real value, unless you are cheeky enough to start with something that would give you a 0. So you can't start with 0, you can't start anything that would generate a 0, but most things are going to work. So I took a guess at 3. I'm then going to create a recursive sequence that says x n plus 1 is equal to 3 take away 2 over xn. So this notation means that for every value of x that I've guessed, if I divide 2 by that, subtract the whole thing by 3, then the next one is going to be my next better guess. And I can actually now start crunching some numbers here and figuring out what comes next. So x1 should be 3 take away 2 thirds. So I guessed 3 to begin with. And let's see, 3 is equal to 9 thirds, take away 2 thirds, so that is 7 thirds. That means my next guess is 7 thirds. But then x2 should be equal to 3 take away 2 divided by 7 thirds. And the calculations here are going to get a little bit tricky, aren't they? But if I calculate that second fraction, that will be 6 sevenths, and 3 take away 6 sevenths. Well, 3 is 21 sevenths, take away 6 sevenths is 15 sevenths. So x3, let's see if I can do this calculation on the spot. I didn't practice this one beforehand. 2 divided by 15 over 7. So reciprocate that one. We get 14 over 15. 3 is 45 over 15. And 45, take away the 14 is nearly 30. What's that? 31 over 15. Now let's check all of these values, because you might recognize the pattern here. 7 over 3 is basically 2 point something. 15 over 7 is basically 2 point something. 31 over 15 is basically 2 point something. In fact, all of these, the numerator is twice the denominator plus 1, which means if we were to now stretch that to infinity, if we take it to its limit, we could be pretty confident that the final value is 2 times infinity divided by infinity plus 1, which, for the sake of argument, we can say that the result has converged on the value 2. So even though we started with 2 possible solutions, only one of them is actually the result of the calculation. Only one of them is the value of the continued fraction, because the way that we define the continued fraction is not with a quadratic, but instead with a recursive sequence that steadily calculates to more and more precision as we go down. And if you wanted to, you could go back and check the very first calculation that we started with, the first sequence I showed you. Let's go back to the top. 1 plus 2 over 1 plus 2 over 1 plus 2 over 1 plus 2 does in fact converge at 2. And that's my fact about the number 2. The number of results that you can get from doing a calculation with a continued fraction is, well, there's only one of the results actually, so I lied.
Yeah, I like that. I really like that.
I mean, you could look at this modulo some prime, and then and I mean
I
that
mean,
might
one
be
could.
great.
We all want
Yeah, yeah.
to.
Well, I mean, so that might kind of explain the 1 plus I story. So if you're working mod 7, which I guess isn't the number of the day, but if you're working mod 7, then when 7 is 0, right, then 3 squared, well, maybe 7 is not a good example. 5, let's think about 5. So if you're working mod 5, then 2 squared is 4, and 4 is minus 1. So 2 kind of plays the role of I, mod 5.
You're
Here.
suggesting that the continued fraction that I thought was broken, that doesn't converge in terms of all numbers if you
Yeah,
restrict it to a modulo
yeah.
environment.
Yeah, that's what I'd like to see that
Okay.
happen. That would amuse me.
For those of you wondering what we mean when we say a modulo environment, this is the clock arithmetic that you might have heard of, where you start counting up to a number, and then when you get past that, we'll loop back round to the start again. Cindy, you had another thought?
There's another link between continued fraction and p-adic number, and maybe it's gonna link to the thing that I'm gonna talk about, like the p-adic and the metric.
I hope so. I think the thing you might be hinting at is the idea of inverting the continued fraction to move some of the complicatedness from the right-hand side to the left-hand side. So, for instance, looking at this first one, x equals 1 plus blah, 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 I could subtract 1 from both sides. In fact, I'm going to go ahead and do that right now. So I could subtract 1 from both sides to get x take away 1 is equal to 2 divided by, etc. And then I could reciprocate both sides as well to get 1 over x take away 1 is equal to 1 half plus 1 over 1 plus 2 over 1 plus 2. I think that's how it's going to work. And then we can infinitely iterate the subtraction, reciprocate, subtract, reciprocate, subtract, reciprocate, and effectively move the entire infinite continued fraction from one side to another, which is not dissimilar to what I think you might be talking about later with p-adic numbers.
Yeah, that's probably what I was thinking about.
And we are back from a very seamless edit. So up next is Cindy. Cindy, what are you going to talk to us today about?
So today, as we all know, 2 is the smallest prime, and as a matter of fact, 2 is the only even prime. So, at the beginning, I was kind of hoping to talk a little bit about um, quadratic residue and quadratic reciprocity, and talk a bit about why is the theorem fails for 2. Only for 2. Let's
I just
start.
think it's funny that people talk about the even prime being two, you know? I
Because
don't
we never
know.
talk about 3 being the only threeven
Yeah,
prime.
yeah, yeah. If we just, it's like the word
Yeah.
threeven is a very good word, but I mean,
Yeah.
I don't know. Anyway,
And also, I think for a lot of the theorems, I don't know, like for a lot of the theorems that we talked about in number theory courses, um, yeah, we mainly kind of just assume like let P be an odd prime. We don't talk
that's
about it.
true. Yeah, yeah. It's like a super common hypothesis.
For
Yeah. So
safety, I tend to start by saying let P be a prime greater than 100, just to cover all of your bases.
yeah, and the quadratic residue and the quadratic reciprocity is kind of like an example of why, like, do we kind of just assume like P be an odd prime? We define quadratic residue as here's the equation x squared equals to a mod p, where we need our GCD of a and p to be 1. We say A is a quadratic residue mod P if this equation has a solution, but P, we're assuming that P is an odd prime. The reason is because, um, for exa for example, if P is an even prime like 2, uh, x squared we can have x squared be equals to 0, 1, and mod 2. And then we have x going to be equals to 0 and x going to be equals to positive negative 1 as well. So like the definition fails for A is a quadratic non-residue mod P if there's no solution. Yeah, so so like this definition does not really hold for 2 at the beginning because 1 and negative 1 they're both equals to each other, which are actually the same thing, which is just 1. Yeah.
I'm not sure I know. So do you want to say that it's just not interesting to think about if X is a square mod 2?
Yeah, like for example, if x squared is going to be equals to um 0 and 1 mod 2, right? Then
Mm-hmm.
um for if we're solving for x squared equals to 1 mod 2, the two solutions are actually the same thing.
Right. Yeah, yeah.
Yeah.
Because X squared equals one mod 2 has,
Yeah,
well,
because
X
negative
squared
1,
equals one mod P has two solutions, plus and
yes.
minus one. Yeah.
Yeah. And so for the term of quadratic reciprocity, um, like we need let P two distinct primes. And then the quadratic reciprocity theorem states that PQ, the Legendre symbol, is going to be equals to -1 to the power of P minus 1 over 2 times Q minus 1 over 2.
Oh, maybe with the other Legendre symbol in there though too. Oh, I see. You're gonna put it on that side. Okay.
Oh,
I always put them on the same side, so it looks like they cancel. It's kind of the joke, but
I see. Yeah. Times the one with flips. And then it's gonna be, well, I mean, it's also equals to um it's also equals to Q over P if P is congruent to 1 or Q is congruent to 1 mod 4. And it's going to be equals to Q over negative Q over P if they're both congruent to 3 mod 4.
I mean, this is a good point maybe to say something wonderful about the number two, because one of the uses of the number two is that with two things you can say yes or no. So you're sort of encoding the yes, it's a quadratic residue, or it's a quadratic non-residue, no, um, with numbers, and then those numbers are being encoded in the Legendre symbol.
Yeah, and also
You want to answer the question, is P a square mod Q? And a normal human being, when asked a question, would say yes or no. But the Legendre symbol answers those questions by saying +1, -1. So you're sort of encoding the yes and the no as numbers. And you can do that because there's two different numbers,
yes,
so
yes, yes,
you've
yes,
got
yes.
two numbers now, and they can encode yes and no in the Legendre
Yeah.
symbol.
Yeah, because maybe I should define the definition of a
Yeah,
Legendre first.
that's a good idea. Yeah.
Yes. So if P or P over Q, this
On
thing,
Q, P on Q, P on Q.
P on how do I do the
Hang on, Jim, are you trying to tell me that this is not just a normal
Not
fraction
a
that's going on
fraction. Yeah,
here?
yeah. So if
Oh
you say
my
P over Q, then
goodness.
I think people
yes.
get scared that you're dividing. So P on Q
Ah, I
sounds like you're not
see.
dividing. Yeah, I don't want to
I
divide.
actually never know how to pronounce it.
No, I don't know how to pronounce anything either because I remember
Okay, so maybe I should talk about the definition of Legendre symbol. This thing, P on Q, it is +1 if P is a quadratic residue mod Q. And it is equals to -1 if P is a quadratic non-residue mod Q.
So without wanting to be the idiot in the room, can we go right back to the top line of this one where you introduce the idea of a quadratic residue? Because I think
Okay.
you two both very much know what those words mean. So my understanding of a quadratic residue would be we take a value, we square it, and then we see what's left over after we have taken a mod of another value. And by mod of another value, we mean this clock arithmetic, where we see how many whole numbers past the largest multiple of a number a square value could be. Is that what you mean by a quadratic residue?
I mean, I mean,
Yeah.
I think the thing that's a little bit different is that when people, it's often not that they're starting with numbers and they're squaring them. They're often prompted with the question, is two a quadratic residue mod 7? And then, it's like that voice in a world where 7 equals 0, in that world, right, 2 is a perfect square, So it's really asking what numbers are squares, and the numbers that are squares suddenly kind of weird because you're working in a world where 7 is 0 if you're working modulo 7. And if 7 equals 0, then 3 squared is 9, which is 2 more than 7. But 7's 0, so 3 squared is 2. So 2 is a perfect square modulo 7, even though in any normal world, right, 2 isn't the square of any whole number. But it is a
So
square
could
mod 7.
so could I have a go at this and see if I've understood what's happening here? So I might pick a number. I'm going to pick a number in my head, and I'm not going to tell you what that number is. But I am going to tell you that if we are dealing in mod 8, then the number that I'm thinking about is 1, and 1 is a square number.
One.
So the number you're thinking about is it is a square mod 8 because it's the same as 1 squared mod 8.
So the number I was thinking about was 25. And if I'm
Hmm.
dealing in mod 8, then I notice that that is one more than 24.
Hmm.
So that
Yeah.
means in mod 8, the number 25 is equal to 1.
Of course, 25 is also 5 squared. So it's
Yeah.
Oh,
definitely a
so we're not
square.
okay, so
Yeah.
we're not necessarily dealing with a square number to begin with.
Well, like 2. I mean, 2 isn't a square as a normal number, I guess, but it is a square mod 7 because it happens to be 3 squared.
Right.
Yeah.
Yeah. Now, of course, I mean, it's maybe more exciting when you think about mod 8. 17 is also 1 mod 8, and 17 sort of isn't a square number in any normal sense, but it is still 1 mod 8, so it's a square mod 8.
Okay, so Cindy, perhaps now that we've understood what the mod 8 refers to and when we count something to be a square when written in a mod, can you tell me about this mod p being an odd prime?
Like our definition is for like p being an odd prime, which is like a prime bigger than 2, because the reason that we don't define for uh like p being 2 is just because if, for example, we're trying to find x squared is going to be equals to 0 or 1 mod 2, then we're both going to have like, for example, 1 is a 1 on 2, the Legendre symbol 1 on 2 is going to be 1 because it is a quadratic residue mod p. Then 1 on like negative 1 on 2 is going to be equals to 1 on 2 is going to be equals to 1 as well. It is also a quadratic residue mod
So you're
p.
telling me the problem that the problem with having p being equal to 2 is that when you're dealing with mod 2, the number 1 and the number negative 1 are the same number.
Yes. Cause like the other part of the I think I remember there's another theorem which is telling us um the number of quadratic non-residue and the number of quadratic residue mod p, they have to be the same. So this fails for mod 2 because
Okay.
like 1 is a quadratic residue and well negative 1 is of course equals to 1 and then 0 mod 2 it is 0. There's another definition like the third part of the definition for Legendre symbol is if A on P is going to be equals to 0, that if P divides A, well, 0 divides everything. So yeah.
Okay. All right. Okay. I think I'm understanding then up to this point. And then the last thing that we can now introduce then is what this Legendre symbol does.
That is the theorem for quadratic reciprocity, which states that P on Q is going to be equals to negative 1 to the power of P minus 1 over 2 times Q minus 1 over 2. And then we can do the flip thing. The reason that the theorem is really useful is because, like, for example, our P and Q, they're distinct, right? And if, for example, we're working with really large numbers, like we can do the reciprocity to make the number smaller so that we can easier, so that like it's gonna make us easier to compute.
I mean,
So
and that is amazing. I mean, because you would never think that you could figure out what numbers are squares mod p.
yeah.
I mean,
Like
that
for
seems like an
example,
unanswerable question.
8,000 something, like it's probably impossible for us to do it like by hand. So if one of the P or Q is 2, that means we're gonna get like 2 minus 1 over 2, which is 1 over 2. Negative 1 to the power of 1 over 2, which is root of negative 1, which is not in real number.
Right. Oh, that's a problem then. Huh?
And that's the example of some of those theorems in number theory, which we like it fails for 2, but works
That's
for all of the other primes.
That's really interesting. And I'll tell you what, that is the first time I've ever had anybody convince me that 2 being the only even prime is significant in some way, as opposed to it just being the same for every value, but we only use the word even. So that's quite a surprising result from what I thought was going to be a very boring fact about 2 being an even prime. So
Okay.
Jim, I'm fascinated by this diagram with the 7 dots. Do you want to tell me about that?
Yeah, so I guess partly from thinking about the prompt of the number 2, and then also thinking about two-adic numbers, I have sort of, I guess, a personal story about the two-adics. So I guess I was an undergrad at the time, and my roommate at the time, Drew, asked me this question about taking a square and dividing it up into an odd number of just congruent triangles. So, one of the special things about 2 is that 2 is sort of the source of the even and odd dichotomy in our world. So, thinking about, can I cut a square into an even number of congruent triangles? You have a square sandwich and you want to share it with your even number of people. And you can do that and give them all the exact same sandwich shape, because like if you got 2 friends, you just cut it down the diagonal. If you've got 4 friends, maybe you cut the sandwich in half and then cut 2 diagonals. So, it's not a problem if you have an even number of people to divide a square up into an even number of just congruent triangles. And then the question is, well, what about an odd number of triangles? Or more generally, if you have a square and you want to cut it up into an odd number of equal area triangles, is that possible even? And my roommate asked me this question. I'm not entirely sure why he was wondering, but he asked me this question. I thought about it for a little while. I didn't make any progress on this. I went to the library. I found that this was in fact shown to be impossible, that you cannot divide a square into an odd number of equal area triangles. The proof of this ends up relating to two-adics, which I think is a huge surprise, because it's the kind of question that you could have asked somebody in ancient Greece and they would have understood the question. But somehow, it takes 2,000 years of mathematical development, to develop something like the two-adics that then sheds light on this particular question. And I want to talk about the whole solution about, for this particular thing. But part of the answer involves the kind of even and odd thing that I think is really joyful. And in particular, my favorite way to show something exists. So the best possible way to show that something exists is to show that you have an odd number of them. Because zero's not odd. So this diagram is a dissection of a square. It's supposed to be kind of a random dissection of a square into triangles, and I've labeled some of the vertices apparently at random, either green, red, or blue. And I do apologize for the choice of green and red, which are not the most easy to disambiguate colors in the world. But there's 3 different colors. There's a green color, a red color, and a blue color. Yeah, it's probably better to label them like G, R, and B. So you've labeled the vertices of this dissection in 3 different ways. And what you'd like to show is that there's a triangle that has all 3 colors, so sort of a rainbow triangle. So this is your goal. And I guess the name for this sort of thing is Sperner's lemma. But how am I going to go about showing that? So the argument ends up being that well, I'd like to say that the number of rainbow triangles, of triangles that have all 3 colors on their vertices, is just the same as something else. And I'm not actually going to show that. Instead, what I'm going to show is that the number of triangles that have all 3 colors has the same parity, so it's both even or both odd, it's the same mod 2, as the number of these pebbles that I've put down. And the little black squares that I put down, these little pebbles that I put down a pebble on either side, if they're inside or just on the inside, if it's the boundary of the square. But I put down a pebble on either side, not outside the square, but either side of any edge which is green and red. Nothing outside the square, though. Okay. So, so now what I want to do is I want to try to count how many pebbles there are and how many rainbow triangles there are. And I can just try to look in each triangle and figure out how much does each triangle contribute to the pebble count. So a triangle that's got a blue, red, and green vertex, that'll contribute one pebble to my count. So that's, I think is there a disappearing highlighter? Yeah, okay. So there it looks like there's two triangles that have contributed a single pebble. Now the other triangles don't have all three colors on their vertices. So the other triangles are like all green, or they're red and green, or maybe they have two blues, and there's none in this picture, but they could have two blues. Those triangles will each contribute either 0 pebbles or 2 pebbles. But the benefit here is that 0 and 2 are both even. They're both 0 mod 2. So if I just add up the total number of pebbles, that's the same as the total number of rainbow triangles mod 2. So in this case, if I add up all the pebbles that I see, it's both even or odd as to whether or not the total number of rainbow triangles is even or odd. Okay. The other thing that's kind of cool about this particular picture is that I could also just count the pebbles by counting the interior line segments or the line segments that are on the boundary. So the boundary line segments that are green-red, they contribute 1 pebble. And the interior line segments, regardless of the color, they contribute either 0 or 2. So that means the total number of pebbles is the same at mod 2 as the total number of green-red edges on the boundary of my cut-up square. So putting that all together, that tells me that the total number of rainbow triangles, the total number of green, blue, red triangles, is the same as the total number of these pebbles that I very cleverly put down, which is the same as the number of green, red edges on the boundary, all mod 2. So if somehow I could end up proving or knowing for some reason that I had an odd number of green-red edges in the boundary, that would guarantee for me the existence of a green-blue-red triangle somewhere in my picture, because I know the numbers of those two things are the same mod 2. So if I know I've got an odd number of green-red triangles on the outside, green-red edges on the outside, then I necessarily have an odd number of rainbow triangles. I necessarily have a rainbow triangle. And that's important, maybe, for some reason. It turns out that if you color these vertices using some way that you measure numbers two-adically, then the areas of these triangles two-adically get related to have some property, and as a result, the existence of this rainbow triangle will force the number 1 divided by n to be 1 divided by an even number, which then guarantees that you can't cut up this square into an odd number of equal area triangles. And obviously that takes more work, but I think this piece of it is very compelling, and it really gets at this. I think just this lovely idea that you prove something exists by showing there's an odd number of them, and in this case, you want to show there's a rainbow triangle.
So you're telling me that as the Sherlock Holmes of maths, you can come up to this room, and without looking in the room, you can see that there's a green and a red post and a wall on this side, and another green post over there. And just by looking at this one wall with these 2 green posts and 1 red post, you know for a fact that somewhere inside this locked room there is 2 triangles that are rainbow colored.
Yeah, that's a much better way of putting it, certainly. Yeah, I mean, that seems very surprising, very unlikely.
That is
now
madness.
here, of course, there's 2, so this picture doesn't really sell it so well, because probably should have had a picture with an odd number of green-red edges. But if there were an odd number of green-red edges on the boundary, then you'd be guaranteed to have a rainbow triangle in the middle.
I mean, so you know the way to test if something that you've built is rigorous, and that is let an idiot play with it for a little while. If I were to take this corner and change it to a ret, so it was green, it's now red. Can we just see how that's going to affect the rest of it? So that means I now delete this box, and instead I put 2 boxes here and here, and 1 extra box here, meaning I've lost 1 and gained 3. So in total, I've added 2, still even. and I've lost one green-red edge and gained one green-red edge. So the
Yeah.
number of green-red edges has remained constant. So I know there
Yeah.
are two rainbow triangles.
Well, you know, there's an even number of
Sorry,
rainbow
I know there's an even
triangles.
number. Okay, so
Yeah.
by
Yeah.
both metrics, both the counting all pebbles and edge
Hmm.
pebbles, still an even number. Okay, so it
But you
works if
could
I change
keep
that then.
going. You could make the other corner. You could make this corner. I'm not very good at this program. Oh, I've failed. Make both of these blue or red.
Well, I
Color
want
knowledge. My
to
color knowledge.
I want to
Or
make this
whatever. I
one
mean,
blue. I want to make this one
okay.
blue and create more rainbow triangles because
Oh, maybe
I
that's
think you've
better. Yeah.
well last week I cheated a little bit by predicting the answer was going to be two and making it two. So I think you've cheated by making two triangles already. So I'm going to make
Yeah.
that one blue, and now you've got an additional rainbow one here.
Yeah. But you
We've
lost
and
that pebble.
we've lost that pebble, and we
Yeah.
haven't provided any more pebbles.
No. So you have one
So
pebble on the boundary.
but now I've got one boundary pebble and three rainbow triangles.
Right. And
Oh,
one
but
is
they're the
three.
same, but they're the same parity, aren't they? Because you're
Same
working
parity.
in mod two. Okay, interesting.
Yeah.
And same for the number of inside pebbles. We've lost one, so they are now an odd number of internal pebbles and an odd number of rainbow triangles.
Yeah, because the parity of the
Gosh.
pebbles is also supposed to be the same as the parity of the rainbow triangles and the parity of the outside green-red
Okay.
edges.
Okay,
So,
I see what you're doing. I see what you're doing.
yeah,
There's one more way I'd like to try to break this, if you don't mind.
yeah, go ahead.
Can I create another triangle here and make this a blue? And
You got to
sorry,
connect it up with edges.
another
Yeah,
vertex, I mean, and make that a
yeah.
blue, which gives me an additional two rainbows.
Hmm.
Doesn't provide any extra pebbles. Ah,
Yeah.
so you're saying I can only, if I add a new edge, I can only ever make a maximum of two rainbow triangles at a time. I can't make
Yeah,
all three of them rainbow.
if you're messing with the interior, yeah, you're not going to be able to affect
Yeah. It's
the total
impossible to
number.
add one here, isn't
Yeah,
it? If
yeah,
that changed to red, green, or blue.
yeah.
That's really cool. I like that.
Yeah, it's a classic thing, but it's Sperner's lemma. This is a combinatorial, and there's lots of other applications of it. But I think specifically there's this two-adic story, which is pretty fun, and maybe I can send you a link to that too. I mean, it's pretty
Is it wrong
entertaining.
to assume that this is related to graph coloring algorithms in graph theory?
Yeah, I would certainly say this is some kind of graph coloring fact.
Because
I'm trying
one
to
thing
think.
I very rarely do in graph theory is also deal with p-adic numbers.
Right. Well,
Cool.
yeah, the gimmick is to try to color the vertices using the two-adic valuation. I'm trying to see if I have a copy of the mathematical coloring book by Seufer. It's like I surely this is in there somewhere. I don't know. Maybe not.
We can all just take out our own copies, I'm sure.
Yeah. My books are in no order, so I can't.
Yeah,
I
I'd
don't
keep mine in
know.
the
But
kitchen.
yeah, I don't know. Anyway, but
Okay.
yeah.
All right, that's great. Thank you very much. That's an excellent fact. Okay, so that brings us onto the next part of the story today, where we're going to be looking at my favorite website, and that is the online encyclopedia of integer sequences. So today, folks, we've got a really exciting one. We are looking at A002222. See if you can guess why I chose that one today. To define this sequence, we are taking AN as the sequence, where n is the term number of the sequence, and this is the number of partitions of 5n that can be obtained by adding together five, not necessarily distinct, partitions of n. So, as with most of my students, I'm going to agree to do the hard part and then let you guys have a go at the easy problems. I'm going to do this when n is equal to 1. So, let's see what is happening then in terms of this definition. We're going to be looking at the number 5n. So, if n is equal to 1, 5n is equal to 5. And I'm looking at the number of different ways that I can construct the number 5 using partitions. So when we say partitions, we mean break the number down, add it back together. So to get the number 5, I have to use 5 partitions as well. So I have to take 5 things that add together to make the number 5. And I'll grab the low-hanging fruit first. 1 plus 1 plus 1 plus 1 plus 1. Oh, and that's it. There is only one way of doing it. So, which of you wants to go first and try the case when n is equal to 2? And which of you wants to have a go when n is equal to 3? Cindy, can I invite you to do n is equal to 2?
Yeah, sure.
So how many ways can you add up 5 numbers? In order
Uh,
to get, what are you aiming for? Aiming to get 10.
10.
And whilst you're thinking about that, Jim, I know you've got a notepad already scribbling away because I can see your eyes. Jim, you're having a n is equal to 3, so you're trying to get to 15. I'll give you a clue, Jim. Your number is going to be a larger number than Cindy's. So whilst these two are calculating away at these results, I'm going to let you, the viewer, have a go yourself. So you've gone for all of the numbers being 2, but I might invite you to think about what happens if this first one is a 1. Then maybe you could do 1 plus 3 plus 2 plus 2 plus 2.
Plus 2, yeah. Wait,
So it's
can
a
we have
combinatorial problem.
we don't have any zero, no?
That's a good question. Um, I'm going to say no.
Okay.
Otherwise, my first value wouldn't be 1.
So we don't have zero. We only have like natural numbers, right?
Only natural numbers.
Okay.
The general vibe of the whole chat show is about natural numbers, despite the title.
Oh, nice.
I am sort of horrified that 0 isn't a natural number, but
Last
maybe
week, we all concluded that 1 was a prime number. So,
oh,
Oh.
I'm not sure. Yeah, I'm not sure I'm happy about that either. But yeah, definitely don't want one to be prime. I don't know. But I also want 0 to be a natural number, so just try to be as heretical as
whilst
possible.
whilst we're talking about the off-topic banter section, I'm of the belief that we shouldn't really start counting numbers until we get past 10 or past 9 at least and go into the next place value. Because
Those are the real numbers. Yeah.
before that, we don't. There's not really any point to them. So I'm sure you guys have both heard about the law of small numbers.
Oh.
Yeah.
Yeah, so loosely for the viewer, the law of small numbers says that there's not enough numbers down down the shallow end of the swimming pool, and so they just have to do quite a few different jobs. Cindy, going back to your fact about the 2 being the only even prime number and that being significant, I might suggest that actually 2 has just got so many jobs to fill because it's doing the binary choice option. It's saying it's either a yes or a no. Jim, you brought that up earlier. So I would say maybe 2 is not interesting that it's the only even prime, but it's the only prime that also happens to do the job of saying yes or no to things. um, so because all these numbers are just clustered together, they've got so many different hats to wear. So
Oh.
have you considered the fact that for 2 1s, for instance, you could have 2 1s, 2 3s, or you could have 2 1s and 1 4. So whilst you guys are still riffing on this, I can see Jim is doing this on mute because he's screaming expletives all the while. I might give you a clue to go and have a look at the online Encyclopedia of Integer Sequences A002221, which does the same thing but replaces the number 5 for the number 4. And actually, there's a whole chain of integer sequences around this code. So 002220 does the same thing, but with 3n and 3 partitions. So the classic strategy in mathematical problem solving is before doing something difficult, do something easy. If you were trying this at home, maybe go back and start with 3n and 3 partitions and then build it up. And you'll notice that there is a pattern that goes between these sequences as well. I'm going to push you for your final answers then. Cindy, you think it's a number bigger than 5, I hope. Do you want to take a punt at what you're going to say?
10?
You're going to guess
Wait,
10, and the answer is
that's a random choice. Oh,
it's 6. It's only 6. Yeah, so you had almost all of them apart from that one extra one that I cued you in for. Never mind. Jim, Cindy took a long time to guess her next value, so you've had a little while to calculate yours. But can I push you for a guess now?
Well, I guess it's 21, but I mean,
Is it just pure guess? Your reputation is staked upon this one.
no, I mean,
It's 21.
but I mean, but I don't have a good sense though of what this number sequence means, I must say. I mean, I don't know. I mean, anyway, I don't know. Yeah, I need more feelings about partitions.
Do you think it's going to grow slowly or grow quickly?
I quickly, guess.
Yeah, I mean, as with
Very
pretty much
quickly.
anything to do with combinatorics, it does grow quickly.
Yeah.
But the
Yeah.
question becomes, what counts as quick? So
Oh.
I would definitely give my year sevens the question up to maybe 21, but I wouldn't expect them to get all 91 partitions of the number 20. And
Mm.
as compared to some sequences we have, this one I'd say grows relatively slowly. That's about what, one digit every two rows.
Yeah, I mean, I guess
Uh,
that's not so bad. I don't. I mean, I guess I don't have a good sense of. I just don't know enough about partitions. Probably is really the truth of it.
It's just adding, isn't it?
I don't know. Well, I don't know. There's all these weird identities. I don't know. There's all people. The partition people know all sorts of facts about partitions. I don't
The
know.
partition, do you know, I tried to go to a meeting of the partition people last week and they wouldn't let me in.
That's, there's all these barriers and walls.
There's all these barriers and they keep changing the
Yeah,
barriers
I
as
don't know.
well. And I was just
I
trying to
don't know.
count all the barriers.
Yeah, it's very difficult to find them.
Hmm.
I don't know.
At least you know where the partition people meet. The prime counting people, you don't even know when their next meeting's going to
That's true.
be. Lovely stuff. Okay, so to round the episode off, we're going to do something that is a new tradition in that this will be the second time we've done it, and that is to take a vote about whether we think that the number two is more interesting or less interesting than the number one. The number one is currently our reigning champion. It's had a two weeks in the sun now.
Oh,
Cindy, do you think number two is more interesting than number one?
Well, personally, I would say like for number two, well, we have like p-adic numbers, we have continued fractions. And that is like the really smallest prime, the first prime. And but I think number one, we also have a lot of interesting facts about number one. Like one is also the multiplicative identity. One is yeah.
Yeah, so last week we did narrow it down to three facts. If you haven't seen episode one yet, go back and watch that now. I'll stay here and wait. But spoiler alert, we looked at Benford's law, we looked at Legendre's constant, and we looked at the sum of the infinite sequence, half plus a quarter plus an eighth, etc. Those are the facts that we're competing against. Honestly, I've no idea how I'm going to summarize our three facts today for episode three in a fortnight's time. But Cindy, what's your vote? What's more interesting, number two or number one?
I'm gonna say, for me, because I like me personally, I'm really interested in like p-adic number and like the kind of like more number theory that thing. So maybe I would say number two.
Going for number two. Fantastic. Jim, what's your vote?
I mean, totally unbiased. Number two, I think.
Uh, Fantastic. I think I have been won over today. To be honest, I went in today thinking number two was going to be a duff one, but I've been
Yeah.
convinced that it is an interesting one. But hey, if you at home are going to agree or indeed disagree, please do so in the comments. Fill those up with all of the favorite facts about the number two that we've missed, that we didn't talk about, or tell us why we are wrong. I reckon that there were at least three arithmetic errors that we've made. Go back and watch this video a second time, see if you can find them, and then rage in the comments because all engagement is positive engagement these days. If you have enjoyed today's episode of Unnatural Numbers, then please like and subscribe and check us out in a fortnight's time. That is 2 weeks' time for those of you over the pond. 2 weeks' time, we're going to be doing the number three, where we will get three new facts from three new guests. Before we go, let's have some plugs and socials. Jim, is there anything that you'd like to tell us about that you're working on at the moment?
I mean, the main thing maybe is just that my secret internet identity is K is one cat. So if you search for K is one cat, you'll find a lot of stuff that I'm somehow connected to.
Is that a social network link or just a
It's I
website?
just the name that I've used since I was 16. It seemed a lot cooler when I was 16, but it's still the name that I go by. So I mean, I've got some stuff
Fantastic. So if you'd
on
like to know
YouTube,
more about
GitHub,
what Jim was
Twitter,
like as a
but
16-year-old,
still posting on K is one cat and various
fantastic. Thank you very
socials.
much. Cindy, is there anything that you're working on at the moment that you'd like to share or a place where people can go find out more about you?
The place yeah, well, maybe my Instagram. Yeah, it's just spelling just Cindy was four Y's and then 0606, which is actually my birthday. So yeah.
Fantastic. And if you could just give us your PIN number as well, we'll be all set to steal your identity. I'll see if I can find those socials and link them in the description below. For me, you can find me on Blue Sky. I'm at mathematicians-pod. And that is because I also run a podcast on maths history. So if you want to find out more about the ancient mathematicians of currently up to Archimedes, then you can go check it out there. Until next time, see you next week. Bye-bye.
Bye.
Bye.
When I was doing speech classes, I was giving a speech about the epitome of something, and then it took my coach a while. That's the epitome. That's a word I didn't know, Or I had one friend who talked about infrared light and that he was misled, but he was misled about infrared light, which is a difference. But I mean, if you're only reading, how do you anyway? But